Thermal Testing and Verification, Part 2. In this part we will address unit, development, and subsystem testing. In Part 1, we introduced the types of tests, test environment levels, and margins applied to space hardware. In this second part, we will explore how such testing is applied at the unit and subsystem level. The various types of tests performed at the unit and subsystem level will be discussed, along with the special role that development testing plays in bringing a design to maturity. We will start with a definition of a unit and show how margins are applied to predicted flight temperatures to establish unit test temperature ranges. Thermal cycle, thermal vacuum, and burn-in tests will be described, along with requirements for such testing on government programs at the acceptance, qualification, and prototype level. The unique aspects of development and subsystem level testing will be discussed. We will first turn our attention to unit level testing. Unit will be defined here as a functional item that is viewed as a complete and separate entity for the purposes of manufacturing, maintenance, or record keeping. Examples include electronic boxes, batteries, solar arrays, valves, and electrical harnesses. As we learned in Part 1, test temperatures are established by applying margins to the predicted flight temperature of the unit or by a default minimum test temperature range. Here we see qualitative comparison of the test temperature range requirements applied by different space system development organizations. The Defense Department and JPL tend to have the widest qualification ranges, which are driven by requirements for a default minimum range. We can also see that margin between analysis predictions and acceptance test temperatures are captured as either analysis uncertainty margin, allowable flight temperature margin, or both, depending on the organization. Next, we see a more quantitative summary of common margins. The margin between analysis and acceptance tests is typically 5 to 11 degrees C, although this may be replaced with control authority margin in active thermal designs. The margin between acceptance and proto-qualification tests is usually 5 to 10 degrees C. Margin between acceptance and qualification test is 10 to 20 degrees, depending on the organization. The first type of unit test we will discuss is the thermal cycle test. Thermal cycle testing consists of rapid temperature cycling in ambient air or gaseous nitrogen. Fans are typically used to circulate the air and modestly increase convective heat transfer. Heating elements and cooling coils are used to rapidly heat or cool the air as needed to achieve temperature cycling. In unit thermal cycle tests, functional testing is performed at hot and cold plateaus to detect possible failures, but the primary emphasis is on environmental stress screening. The types of failures found in thermal cycling of electronic equipment include loose connectors, defective solder joints, inadequate stress relief, performance drift, and material deficiencies. A sample unit thermal cycle test profile is shown, in which the unit is cycled between hot and cold, holding at each plateau for 6 hours on the first and last cycle, but only 1 hour on the intermediate cycles. The unit is continuously powered, except for brief periods at each plateau. The specifics of these unit level tests will vary from organization to organization, so the profile seen here should be seen as one of several commonly accepted practices. When at a plateau, most organizations define dwell as the total time spent at the plateau temperature. MIL Standard 1540, however, defines dwell as just the time at the plateau temperature allocated to allow the unit internal temperatures to stabilize. MIL Standard 1540 calls the total time at the plateau temperature the soak period. It's important to bear this distinction in mind when working on DoD programs. The next kind of test we will discuss is the unit thermal vacuum test. Unit thermal vacuum testing demonstrates the ability of the unit to perform in an appropriate thermal environment as specified by temperature and vacuum. The basic difference between thermal cycle and thermal vacuum is the vacuum environment. The vacuum environment is representative of flight conditions because convection is eliminated, leading to higher part temperatures and more accurate temperature gradients than would be seen in thermal cycle testing. In addition, vacuum-sensitive parts will be appropriately stressed. While temperature cycles are performed in thermal vacuum tests, the primary emphasis is performance verification. The thermal vacuum test demonstrates that unit performance is within specification in hot and cold thermal environments and is accomplished through extensive functional tests performed at hot and cold temperature plateaus. Functional testing is also sometimes performed during temperature transitions. Conduction-cooled equipment is generally hard-mounted to a thermally controlled heat sink and the component covered with a multi-layer insulation blanket. Radiation-cooled or conduction and radiation-cooled equipment is typically tested with conduction heat transfer to a thermally controlled heat sink and radiation heat transfer to the surrounding environment. The conductive and radiative portions of the heat transfer should be controlled to the same proportion as calculated for the flight environment. Thermal vacuum testing must, of course, be conducted in a vacuum chamber. The chamber should have a vacuum capability of 10 to the minus 5th torr or lower. Heating and cooling capability is provided by the chamber walls, cold plates, ancillary heaters, and lamps. We will now explore unit test requirements levied on government programs in more detail. NASA Goddard, JPL, and DoD all have acceptance and either qualification or proto-qualification temperature margin requirements. While JPL, Goddard, and DoD each bookkeep the margin between flight predictions and acceptance differently, they all effectively require some amount of temperature margin between analysis and tests. JPL and DoD also have default minimum temperature ranges to ensure design robustness. While the exact numbers and accounting approach are a bit different between organizations, the concepts are largely similar. In addition to temperature range, government organizations also levy requirements on the minimum number of temperature cycles, the minimum dwell time at each plateau, and the rate of temperature transition. MIL Standard 1540 requires substantially more temperature cycles for units at the protoflight and qualification levels than does NASA. It should also be noted that the actual dwell time at plateaus may have to be longer than shown here in order to conduct the required functional tests. When conducting thermal vacuum tests, it is important for units to be on because effective screening is only accomplished when the unit is operating. Functional tests must be performed at hot and cold plateaus for performance verification. Operation during transitions to plateaus is required to test workmanship over the full temperature range. Hot and cold starts should also be performed after a brief soak period with the unit turned off. Most organizations have requirements for burn-in testing, which is a continuation of thermal cycling, but without functional testing. It is often performed as part of thermal cycling with the objective of accruing additional hours of operation under thermal stress. Each organization has different specific requirements for total burn-in time, at what level the burn-in must occur, and how many failure-free hours must be demonstrated. As with anything else in life, there are always exceptions. Generalized test requirements don't always work for every type of unit, so waivers and exceptions to the rules are common. Some units, like batteries, would be damaged if exposed to the fully margined or default minimum temperature ranges specified in government test requirements. Hydrazine freezes at 2 degrees C, making functional performance requirements for some propulsion components below that temperature superfluous. The expense of requalifying units that have previously been qualified for another program may not be warranted. Due to these practical considerations, the actual test temperature ranges for many components on any given spacecraft are likely to vary from the generic or ideal test temperature ranges. While the thermal test philosophies engendered in government test requirements are heavily oriented to the testing of electronic units, with some modifications, the same approach can be applied to other units, such as moving mechanical assemblies, antennas, solar arrays, and batteries. These units have special requirements that demand careful test planning. MIL Standard 1540 contains explicit guidance on the applicability of thermal testing requirements to different kinds of hardware. It requires both thermal vacuum and thermal cycling for electronics, and at least thermal vacuum for most other kinds of hardware. Since the main purpose of thermal cycle testing is to stress electrical connections, its applicability to testing of components containing few or no electrical components requires evaluation on a case-by-case basis. Moving mechanical assemblies can be extremely temperature sensitive and may be sensitive to temperature gradients. Differences in coefficient of thermal expansion of the different materials in a mechanism may cause binding, and lubricant effectiveness may change torque characteristics at extreme temperatures. To address these issues, JPL and DoD require thermal vacuum testing of mechanisms at the qualification and acceptance levels. Motion performance should be demonstrated at hot and cold temperature extremes in the course of this testing. Motion performance should also be demonstrated while simulating any severe thermal gradient conditions or temperature transitions that are expected to occur in flight. Deployment mechanisms and bearing assemblies are particularly vulnerable to these conditions. Clearance and binding problems can occur in deployment mechanisms at temperature extremes and under temperature gradient conditions. Bearing friction can be highly dependent on temperature gradients, including temperature gradients from the inner to outer races of the bearing. Antennas experience wide temperature excursions and rapid rates of temperature change because they are low mass and have high surface area, directly exposed to external space environments. JPL requires thermal vacuum testing at the qualification or protoflight level and at the acceptance level. DoD requires thermal vacuum testing at qualification or proto-qualification level only for performance verification and design demonstration. A number of actions should be taken to ensure an effective test of antenna systems. High-power antennas should be tested with transmitter power on to investigate solder joint integrity and material state changes. Materials, bonds, waveguides, radio frequency or RF interfaces, substrates, and paints should be subjected to vacuum and temperature-induced stresses. Perceptive RF performance parameters should be monitored during the test to the extent practical, although this may be difficult in a thermal vacuum test environment. For some designs, the shape of reflectors must be measured before, during, and after test to determine if shape changes are great enough to affect RF performance. Like antennas, solar arrays experience wide temperature extremes and rapid rates of temperature change on orbit. Testing is usually performed on a small section or coupon of non-flight solar array to demonstrate compatibility with this stressing environment. A representative life test for a solar array at a geosynchronous satellite with a 10-year design life might include temperature cycling of a coupon for 1,700 cycles over a range of -175 to +55 degrees C. DoD requires thermal vacuum testing of solar arrays at qualification or proto-qualification level, with thermal vacuum or thermal cycle testing being optional at acceptance level. The DoD does permit thermal vacuum only, but thermal cycle testing may be beneficial, especially for workmanship screening. This is because convective heat transfer in thermal cycle testing can induce a more rapid rate of temperature change than can be achieved by radiation in a vacuum. This subjects the materials, honeycomb, substrates, films, cells, wiring, and backside paint to greater temperature-induced stresses. Batteries are highly sensitive to temperature. At high temperatures, their performance and life can degrade, while electrolytes can freeze at low temperatures. Batteries can also explode at either excessively hot or cold temperatures. Because of their sensitivity, tight temperature control, often at relatively low temperature, is required for batteries. In many cases, this control is achieved using dedicated radiators with heaters or variable conductance heat pipes. Even with such designs, temperatures may still rise modestly during high discharge or charge periods when internal waste heat generation is high. Thermal analysis uncertainty margin in the form of temperature often can't be applied to batteries because the margin would be large compared to the allowable temperature range. However, equivalent margin may be achieved by cold biasing the design and using oversized heaters or variable conductance heat pipes to control the battery to within the desired range. Batteries usually have requirements to limit cell-to-cell temperature differences within the battery. Meeting such requirements can be challenging because battery packs often have complex designs with many thermal interfaces. Thermal conductances across these interfaces should be verified during battery-level tests under realistic environments. DoD explicitly requires thermal vacuum testing for batteries at qualification and acceptance levels, but thermal cycling is not required. Before moving on to the topic of development testing, let's recap some key takeaways from unit-level testing. We have seen that there are three kinds of unit-level tests: thermal vacuum, thermal cycle, and burn-in. The objectives of these tests include environmental stress screening and performance verification of the hardware, plus survival and turn-on demonstration at extreme temperature. There are two levels of testing: qualification testing that verifies the hardware design at temperatures greater than expected in flight, and acceptance testing that verifies workmanship and flight worthiness at flight-like temperatures. Thermal cycling, with its rapid temperature transition and many cycles, is effective for environmental stress screening. Thermal vacuum, with its vacuum environment and temperature cycling, is effective for demonstrating performance and survival and turn-on capabilities. We will now proceed to the topic of development testing. Development tests, also known as engineering tests, offer many benefits to the design development process. They validate new design concepts or the application of proven concepts and techniques to new configurations, assist in the evolution of designs from the conceptual phase to the operational phase, reduce the risks associated with new flight hardware, and help investigate problems or concerns that arise after successful qualification. The primary objective of development testing is to identify problems early in the design phase so that any required actions can be taken prior to starting formal qualification testing. Identifying problems early means less disruption to program execution, thereby minimizing schedule and cost impacts. Development tests also confirm structural and performance margins, manufacturability, testability, maintainability, reliability, life expectancy, and compatibility with system safety. Development test requirements depend upon the maturity of the subsystem and its operational requirements, as well as the intent of the test. Where practical, these tests should be conducted over a range of operating conditions that exceed design limits in order to identify marginal capabilities and design features. Common thermal development tests include unit or subsystem thermal balance testing, deployment mechanism testing, and heat pipe tests. Thermal balance development tests have two principal objectives: to obtain thermal data for the verification of analytical thermal models, and to verify thermal control subsystem hardware. Thermal balance tests are performed in a thermal vacuum chamber on flight or flight-like equipment. They can be performed on everything from individual units to full spacecraft. Hot operating, cold non-operating, and sometimes hot non-operating steady-state conditions may be simulated, along with transitions between temperature levels, to provide the data needed to evaluate design performance and check thermal math models. Equilibrium temperatures and repeatable heater cycling data are recorded for both the test article and boundary conditions. Deployment mechanisms are critical to mission success. Failure to deploy a solar array, for instance, typically results in a complete loss of mission before it has even started. Improper mechanism operation is one of the top causes of space mission failure. Mechanisms are also often mounted external to the vehicle where they are stressed by extreme mission environments, making proper operation all the more challenging. It is common for development tests to be specified for deployment mechanisms to demonstrate operation under conditions of vacuum, temperature, and changing environments. To minimize mass, some deployment mechanisms are designed such that they can only support the mass of the deployed component in 0G. In such cases, special fixtures may be needed to offload the deployed mass during ground testing. Some typical concerns that are investigated during development testing are differential expansion of materials causing a failure to deploy, thermal gradients within the mechanism causing binding during deployment, and thermal degradation of materials, adhesives, or lubricants at extreme hot or cold temperatures. The high reliability of heat pipes is primarily due to the numerous development tests that heat pipes are subjected to. These tests check for leaks, verify weld integrity, and demonstrate functional performance. A primary consideration for early testing of heat pipes at the unit level is that they must be in level orientation for performance verification. A tilt of 1/10 of an inch or less over the length of the heat pipe is often required to avoid performance degradation. This is not always possible at higher levels of assembly, making testing at the unit level vital. A typical heat pipe development program might include verifying function and measuring the effect of tilt in a 1G environment during development, burst pressure, radiographic, proof pressure, leak, and transport capacity tests at the heat pipe level, and functional performance, static load, acoustic, thermal vacuum, leak, and working fluid load tests at higher levels of assembly. We will now move on to the next topic, testing at the subsystem level. Subsystem and payload level testing is performed after unit level testing, but before spacecraft level testing. The objective is to satisfy spacecraft level requirements in a configuration or environment dedicated to the needs of the subsystem under test. The advantages of testing at the payload or subsystem level include accomplishing the test in a smaller, less expensive facility, tailoring the environment to the subsystem with no interference from adjacent subsystems. The boundary conditions are well understood. It is easier to obtain data for model correlation. It is easier to isolate problems. Instrumentation can be significantly more thorough than at spacecraft level. And overall program costs can be reduced because problems are resolved without impacting the schedule critical path. Acceptance, protoflight, and qualification temperature ranges are the same as applied at unit level. In practice, however, temperature cycle range experienced by many units in a subsystem test is less than they experience at the unit level because some units within the subsystem reach their allowable limits first, preventing further temperature excursion. But such restrictions are generally less pronounced at the subsystem level than they will later be during spacecraft level testing. As is the case at the unit level, government organizations have specific requirements for subsystem level testing in regards to the number of cycles, dwell times, and temperature transition rates. The number of cycles is typically in the 4 to 10 range. with specified dwell periods at each temperature plateau. Temperature transition rates are also sometimes specified, but may be limited in practice to the maximum rate that the test chamber can achieve. The Air Force's Millstar communications satellite provides an example of the advantages of conducting a subsystem-level thermal test. There is an EHF antenna enclosure on Millstar that would be difficult to adequately test at the spacecraft level. The enclosure, shown here, has a heat pipe network that transports waste heat from the internal antenna electronics to a radiator on one side. The enclosure is covered with multilayer insulation blankets, except for two sides, one of those being used as a radiator, and the other covered with fibrous refractory composite insulation. Testing at the spacecraft level would be difficult because the required heating lamps would interfere with adjacent payloads, the heat pipes in the enclosure would not be level and would therefore not work properly, it would be difficult to install instrumentation that would be needed to correlate thermal math models, and there would be limited opportunities to do functional testing. A subsystem-level test provided a solution to these testing issues. The radiator side of the enclosure was removed and rotated 90 degrees so that the heat pipes on the radiator would be coplanar with the heat pipes in the base and level, enabling proper operation in a gravity environment. Multilayer insulation was used to cover the opening left in the enclosure when the radiator was rotated down, and aluminum plates, cooled by liquid nitrogen and warmed by electrical heaters, were used to simulate radiation boundary temperatures that the enclosure would see when integrated with the spacecraft and exposed to the flight thermal environment. With this approach, flight conditions could be accurately simulated, a full complement of test temperature sensors installed, and all functional testing performed without interactions with other payloads. In Part 2, we have seen that the principal thermal test at the unit level is temperature cycling in air or vacuum. We have described how margins are applied to expected flight temperatures to establish acceptance and qualification test ranges. We have seen that development and subsystem tests reduce program risk by identifying problems early. Requirements for minimal test temperature range, number of cycles, and total test time, commonly limited by government organizations, have been summarized and compared. This concludes Part 2 of the NESC Academy lesson on thermal testing and verification. In Part 3, we will focus on spacecraft level testing and verification.